Thank you for inviting me to talk in this series. I think this is a great topic, underground storage and utilization, and I'm assuming not going to be just focused on CO2. An aside, a little bit of history about me. I started with underground storage and utilization at the Yucca Mountain site. So I started looking at geologic storage many years ago for nuclear waste. But today I'm going to talk about a more present topic. And as you know, as many of you might know, we've had a long time of CO2 sequestration activity happening in the Illinois Basin. And so today the title of my talk is Surface Structure Interpretation Using Active and Passive Seismic at the Decatur, Illinois CO2 Sequestration Site. So before I start, get into the talk, I want to acknowledge my collaborators. The top three are at the Illinois State Geological Survey. Hannes Litaru, who did a lot of the seismic interpretation, the active seismic interpretation. Robert Bauer, geomechanicist, an engineering geologist, and he did the talk 2 weeks ago, just prior to this. So I'm hoping that some of the things I talk about today sort of springboard off of things that Bob introduced. And Sally Greenberg, who's the PI, who I wanted to thank for pulling me into this project, because it's a really interesting project. Wade Zalewski and Schlumberger did some of the structural modeling, and Francis Stanek from the Czech Academy of Sciences helped us out with the microseismic interpretation. He's now at the Colorado School of Mines. All right, so the geologic setting here is this blue polygon here is the outline of the Illinois Basin. The contours you see there on the top of the basin. And so you can see the Illinois Basin encompasses most of Illinois, a little bit of Indiana, and some of Kentucky. And the contours, the dark parts, are the deepest part of the basin. And down here is where there's more structural complexity. This black square right here is where is the location of the site. And I just want to go over the geologic column real quick. So this is an oil-bearing basin. Most of the oil's sort of in the south. And so these layers that I've identified here are in the context of sources and sinks. So a sink would be somewhere where hydrocarbons might be stored or present. And the seals, there are a number of seals in there that are shales. And for this project, our target was the Mount Simon sandstone, which is a sink, or it's not a source because it's not hydrocarbon bearing. But I think the important point I wanted to make here is that there are 3 shale seals above that. So we expect that this will be a very safe place to contain CO2. And a little bit about natural seismicity. If you still remember the previous slide, this is the same Illinois Basin outline. The purplish to light pink and yellow dots here are natural earthquakes, historical natural earthquakes. And they go back all the way back to 1795. And some of these earthquakes are located and recorded before there were any sensor networks out. So it's based on newspaper articles. How did people feel it and where did they feel it? And so some of those earlier magnitudes are estimated. The 4 here that I have source mechanisms for are relatively recent earthquakes. You can see most of those are strike slip, and that's consistent with the stress orientation that we see in the Illinois Basin for places where it's been measured. Here again is the location of the site, the Decatur site. This blue line right here there's 4 seismic lines that go through the site. I'll show you that in detail in a minute. And the point I wanted to make with this slide was if you draw this radius here of about the circle here of about 100 kilometers radius, you're in an area that's relatively low natural seismicity. And these 4 events are the largest events that have happened in this area. They're all within 100 kilometers of the IDP site. And the largest event in that's within 100 kilometers has a magnitude of 2.7. So we're still looking at the maybe just barely felt range of natural seismicity there. This one's a little bit bigger, but it's more than 100 kilometers away. Now, this is an air photo of the site, and I just want to show you where the wells are. The first injection well, CCS1, is here, and next to that is a geophysical monitoring well, which is where the geophones, the downhole geophones are that monitored most of the micro-induced seismicity. This monitoring well has a bunch of pressure gauges in it, and there's 2 injection wells, because there's actually 2 different projects going on that have gone on here. One of them's not injecting anymore. This one has stopped injecting. The CCS2 well is still injecting, and there's another geophysical monitoring well there. And then here's another verification well for measuring pressure and CO2, things like that. And the next slide I'm going to show you is shows well logs from these 4 wells, the 2 injection wells and the 2 verification wells. So the right log is the permeability, the left log is porosity, and then this log on this other track is gamma ray log. And what you can see, the black rectangles here are the perforation locations. This well right here is the first injection well, CCS1, and here's CCS2. And so that line I just showed you, CCS1, verification well, CCS2, and VW2 are the 4 wells that we primarily use to characterize the reservoir. And the red zones for the permeability and the porosity show where the best reservoir for injection occurs. And the Mount Simon zones that we chose have average porosity of up to 22%, and sometimes the permeability is up to a Darcy. So it's a really good reservoir for putting a lot of stuff in it. All right, so after dealing with seismologists a lot about seismic data, and a lot of my experience comes from oil and gas, it's a lot of times when the oil and gas geologists talk about seismic, they just say seismic data, and we know what we're talking about, reflection seismic. Seismologists have another term to distinguish the two, and that's active seismic. So the active seismic is when you have to create a source in order to get a signal or a reflector or things like that. And the passive seismic is where you wait for the source to happen and then you image it. So what I'm showing on this slide is both. The grid that you see here is the 3D active seismic survey grid. It's an odd-shaped grid because we have, you have to, it's a populated area, so you can't put the geophones everywhere. These blue lines here are the 2D lines that are near or go through the site, and the yellow squares and the red triangles are the passive seismic monitoring locations. So these are seismometers on the surface. The yellow ones were installed by the USGS. The red ones were installed by the Illinois State Geological Survey. And the black dots again are the wells, the main wells, the injection wells, and the verification wells. And right here is the geophysical, the GM1 well, and this is the other passive seismic monitoring, which has 31 downhole geophones in it that collected most of the microseismic events that we see here. These blue dots that are the epicenters of the events on the surface. And as you can see, and I'll talk more about this later, as you can see, they form these clusters. They're not happening everywhere, so we're interpreting those to be probably reactivated faults in the subsurface. All right, so a little bit more about the active seismic. We reprocessed the active seismic in 2019. This was the first processing. And so when you look at the first processing, I think most of you would agree that it'd be kind of tough to definitively identify faults in this. You see some topography here, but whether there's offset or not is really tough to say. So our interpretation of that was that, you've got, if there's faults there, the seismic resolution is at or below, the displacement on those faults is at or below the seismic resolution. So you can't, that's why you can't see it. So the wavelength is too long to be able to see where the displacement is. So we went back and had it reprocessed to try to increase the resolution. So it was in our, you know, our goal was to try to see if we can do an imaging that would identify these faults. And so maybe now you can see certain things going on in the subsurface here. These are the wells, this red part, this red marker right here is the top of the basement. And right above that is the Mount Simon, the reservoir. All right, so since we think we see faults there, I'm gonna zoom in there so you can see how tough our task was to try to map these out. In this case, it seemed even more complicated because all the microseismic events are below the basement. So again, right here, around this location right here is the basement, and all the places where we see microseismicity are in the basement, and we can't see anything that looks like faults in the basement because you don't have enough impedance contrast between the layers. Now, as I mentioned in the previous slide, the events formed these clusters that we interpret to be possibly reactivated faults. Again, they're mostly in the basement. When you see this in the depth view here, this is the top of the Precambrian basement, and 90% of the events are in the basement. A few of them are a little bit shallower, but almost none of them are in the Mount Simon reservoir. These events, these clusters are numbered roughly in the order that they occurred in time. So the first injection well is here, and you start to see microseismicity a few months after injection starts. Injection started in November of 2011, and it actually started happening further away from the well than it is now. So we're trying to understand what's causing the events to trigger, and whether, and it's not a direct correlation between, there's no one-to-one correlation between where the fluid is and where the pressure is to where the microseismicity occurs. And I have some more slides to explain that better later. But anyway, I just wanted to point out that these clusters are spaced out in time. Bob Bauer went over this last week, 2 weeks ago as well, in time and space. So this histogram is roughly 1 month at a time. So you see that there's some months where there isn't very much microseismicity, and then other months you get a big burst of microseismicity. And I want to draw your attention to this month right here, 4. That's the microseismicity that happened in this cluster here. So just quickly, I'm separating all the data into 3 injection periods. This is injection at CCS1 well, which ended November 26, 2014 after 3 years, and 1 million tons of CO2 was injected. And a little over 2 years, there was no injection. And then in April 2017, after a number of delays, but it was kind of good that we had this, because we ended up having a better data set to examine. Injection started in the second well, in the CCS2 well. An injection in this well is at a higher rate, and the target injection is up to 5 million tons in 3 years or longer. So this one is still going on. And I want to drill down into what's happening temporally for these 3 injection periods. So when you first start off the injection, here's those same months, the histogram for the same months here. This is the period of injection in CCS1. And as I said, there was no microseismicity in the beginning, and then all of a sudden, boom, there's a lot of microseismicity, induced seismicity, I should call it. And this is down here, I'm showing the injection rate in tons per hour is the blue line. Injection pressure is the orange line and dots, and downhole pressure is the gray. And these are showing pretty much, fairly constant here which I think illustrates that, you know, we didn't have a big increase in injection when this happened, and then stop, you know, reduced injection and then increase again. It's having to do with what's happening in the reservoir in response to sort of a pressure front going through. And in the non-injection period, there was still seismicity, induced seismicity. You can see it sort of dies, takes a few months to die down, but then it goes to this really low level and stays there. And then when the second injection well comes on, the level does not increase, essentially, even though the injection rate is 1.7 times the injection rate of the first well. And these are the points, the seismic events that occurred during the injection of the second well. So we wanted to understand why this was happening. There was something really significant about this. And because we saw so much induced seismicity in the first well, there was, I'll get to it later, but that sort of influenced where the injection zone was finally placed in the second well. So this is back to the active seismic, and this is a porosity inversion of the seismic data, where it's constrained to the well logs, the porosity that we have in the well logs, and we correlate that to the seismic character of the seismic data, and the low porosity zones are in blue. So here, this is blue is basement, the lowest porosity is igneous rocks here, and then this blue up here is the top seal, and the red is the highest porosity, and this is the Mount Simon formation here, and this gray line is the top of the Mount Simon. And I'm going to zoom in where I have this little arrow here. The black dots are the microseismicity, and where this little arrow is, sorry, I zoomed in somewhere else, but where this little arrow is, it's important to note that there's this layer here that we've called the Argenta, which is a lower permeability, and we think it's a different formation from the Mount Simon. It may be acting as a bottom seal. So in this case, it may be more difficult for injection in the Mount Simon or fluid pressure in the Mount Simon to get to the basement where this occurs. But right here, there are places where this doesn't occur. So that could possibly provide a pathway of microseismicity to the basement. And as you can see that there is microseismicity there around this well. We also think that the other influence that we see in here is these little green areas on the permeability log are very low permeability sort of lenses, and they're probably discontinuous, and because you can't correlate them, and but they seem to be ubiquitous. And those things must be influencing, restricting vertical flow and influencing horizontal flow. So we think that it's possible that injection down here, which is where the injection zone from Mount Simon might have been, well, it was restricted for some reason, but maybe these baffles are the reason, was restricted, pressure increased below these baffles and didn't increase above these baffles until later in the injection period. And this is a little more, I want to return to this to sort of illustrate that. Here's all the layers. This Argenta is what you could call a bottom seal. And here's the Mount Simon zone. And these black rectangles again are the injection zones. And this is where the pressure gauges are. Here's the mudstone baffle that we think really influenced pressure during the first injection in the first well that may have been part of the reason that fluid pressure and CO2 got into the basement. And then if you look at these, the permeability logs, you can see that there's a few other, these things are all over the place. So there's a lot of these sort of, we call baffles, mudstone baffles. And just to sort of further illustrate that, these three pressure ports here had the highest increases during the CCUS1 injection. So during the first well injection, the pressure increased the highest here. During the second well injection, the pressure increased the highest here. So this is more shallow. So that suggests that whatever these horizontal things are, there's a horizontal constraint here that's causing the pressure to increase to sort of the fluid and the pressure to stay in sort of restrained horizontally. So the reservoir heterogeneity here was a lot more important in a smaller scale than we actually expected originally. So just so you can see that a little better. And the last point I wanted to make with this slide was, if you look at the bottom of the injection zone for the second well and the top of the injection well for the first well, there's less than 50 meters of difference in depth here. So there are a lot of rules of thumb that you don't want to inject near the basement, because if you're near the basement, then you'll cause induced seismicity. But in this case, we're still near the basement. We're only, we're less than 50 meters shallower, and we're getting almost no induced seismicity with a much higher injection rate. So let's go back to the fault interpretation, because we think this has something to do with what we're seeing with the induced seismicity. And these are the faults that we interpreted from the seismic data. These green lines here are sort of their cross-section across there. And as you can see, those faults don't actually correlate with the with the induced seismicity. They're not necessarily at the same orientation, but they're sort of, some of them are sort of in the same place at this, but they're not the same orientation. And this is, sorry, this red line here is this seismic line. They're the same sort of length though. And when you drill down and look at individual clusters, this is the same, like the cluster 4, the really big cluster that formed in the first year of injection. There are some subtrends within these events that appear to be parallel to the faults that we have mapped. So these lines here, these darker lines here, are showing the trace of the faults as they cut the top of the Precambrian. This is the top of the Precambrian. You can see the little bit darker blue dots are the events that are above the Precambrian. Everything else is below. And so one way to interpret this would be to say that maybe these clusters aren't really individual faults that are that length, but either they're a fault or composed of a series of fault splays. Because if you look at these clusters in really tight time clusters, and right here I'm looking at 6 hours at a time, you can see that within a day you have these clusters that separate, that identify probably one are sort of following one fault plane. And it's a much smaller fault plane than the whole cluster. And another thing to look at, I mentioned this earlier, is time versus distance. These events are colored by time, just so you can kind of see how they started to play out. Green is early time. The darkest green is sort of around here, right? So it's not even, if this is the well, it's not these down here, these came later. And then as it goes on, there's some lighter colors, and then the purple ones are the latest events. So this is the last cluster to form right here, the furthest one away. And that could be because of, there's migrating out away from the well. This plot is colored by distance from the central receiver, which is right next to the CCUS injection well, and the darkest green. These are actually the darkest green. They look lighter because the outline of them is lighter. But these things you can see where, how far away things are. So this is just distance. You can see how far away things are. Purple is the furthest. So these two things don't correlate at all, as I mentioned before, and I just wanted to show that with here, time versus distance. So if we want to, one of the things that a lot of people do when discussing CCS injection activities is try to compare it to wastewater injection to think about the risk of induced felt seismicity. And so what I put together here was a little chart of injection rates that I pulled out of the literature. The top two are the two wells in the Illinois Basin Decatur area. And we had the injection rates, as you can see, are similar. So we've got the second well is 2,000 cubic meters per day. The injection period is after 3 years, yes, there is a lot of induced seismicity, but it's not felt seismicity. The second well has a little bit of induced seismicity, higher injection rate again, but it's also not felt seismicity. But then when you look at these wastewater wells, we're in this East Texas wells here. So a typical injection rate could be 2,000 meters per day, similar to the CCUS well in Illinois. And after a year, they've got an earthquake of 4.8. That's definitely felt seismicity. So all the reds are felt seismicity, but then something different is going on in the Williston Basin, which is over 3,000 meters per day after a month for injection for a month or more, and no felt seismicity again. So there's a number of things going on that make a difference here. Of course, whether there are faults in the subsurface makes a difference. Whether your faults are in the basement makes a difference. The Williston Basin injection is very deep, but still maybe not very far, not very close to the basement, but it also, similar to the Illinois Basin area where we're injecting, doesn't seem to have a lot of large faults. So that was one of the things that I wanted to, that I thought was, you can compare those two, and a possible explanation for why we're seeing a lot of induced seismicity, but it's not felt seismicity. And in other places with wastewater injection, you see a lot of felt induced seismicity. And just to make sure that everybody's still on the same page, I should have showed this before. I keep saying microseismicity because we are in the microseismicity range here. So -3 to magnitude 1. And just for reference, you can see what the relative energy is, not in magnitude, but something that people can relate to, right? So I just wanted to throw that in to make sure that we, everybody understood what a magnitude 1 earthquake was like. All right, back to the comparisons and issues for wastewater disposal and carbon sequestration. Again, we had volumes of 800 to 2,000 or more than 3,000 cubic meters per day, and many felt events. Some of the issues that you would worry about there would be dispersal groundwater contamination and water rock interaction. And in both cases, you need to know whether you have enough pore space to maintain the injection without causing earthquakes and contamination. But the big point here that I wanted to make, I think, is that the reservoir pressure increases linearly with H2O injection, and that's not necessarily the case when you're injecting supercritical CO2 because it behaves like a gas. It also dissolves in the water after a time, and in some conditions, the water saturated with CO2 can be denser than the brine, so you don't have to worry about the saturation, the risk of things going up, but maybe they go down, which is close to more like what happens to wastewater disposal. But water rock interaction could help you here, or it could hurt you, depending on whether it's locking up CO2 or occluding pore space. So I just want to finish with sort of a summary of what I think we learned about CO2 injection in Illinois. And I think one of the main points was that I've mentioned already is that we have seen impactful reservoir heterogeneity at a kilometer scale. We're not talking about many kilometers, you're talking about a kilometer or less, or maybe 2 kilometers. And even the meter scale vertically, because I remind you that the second well is injecting at a much higher rate and not causing the same amount of induced seismicity. And like other places, the induced seismicity is in the basement, but it's small, and we've interpreted that to be because there are small faults present. Some places there is no hydraulic connectivity to the basement, and that we think that's because of this bottom seal not being present, but some places it is present, and also the horizontal baffles that restrict vertical flow. The one thing that people like to do or want to do before, while you're doing reservoir characterization, is to try to use your active seismic or your reflection seismic to to characterize the reservoir and see where you might have faults as a risk. We had a really hard time doing that. So it wasn't that useful for identifying the reactivation risk, but maybe that's a good thing, because maybe what that means is that the faults weren't big enough to have a significant reactivation risk. And I want to acknowledge the people who funded this project. So the Midwest Geological Sequestration Consortium. It was funded by the DOE, and we have carbon safe projects going on that this is also contributing to. And I also wanted to thank Petroleum Experts and Schlumberger for their software donations that we use to do the geological modeling. Thank you very much.
Sherilyn, thank you very much for your interesting presentation. I'm sure that you'll be happy to entertain any questions from the participants.
The first question is, what are the ranges of induced seismicity magnitude? Approximately -2.2 to plus less than 1.2 magnitude. Right? The second question is, could you give more detail on the characterization of the porosity and permeability, tools and correlations used? We used well logs. We also had a lot of core. So we had core permeability and porosity measurements. And that was used to constrain the model for the well logs. And if you're talking about the seismic data, the porosity inversion for the seismic data, that was based on the well logs and correlating the well logs to the attributes of the seismic data. And we didn't do that internally. We hired a company called Sterling Seismic to do that. And they did a really nice job where they explained us how they were using machine learning to develop a model that was predictive. And it looks like a pretty good match to us. The thing that I thought was sort of exciting about it was that it clearly shows this bottom seal layer and where it might not be present and where it is present, and it correlates with where we see more micro-induced seismicity. The next question is, could you give more detail on the, oh, sorry, that was the same question. Let's see. How much does gas compressibility factor into the differences in seismic response relative to wastewater injection? I don't know. I'm just raising that as a question because I think that that's something that I would love to see people look into. How were the fracture planes constructed from the seismic events recorded? Well, we did not, and what I showed in this talk was not fracture planes constructed from the seismic events. A lot of people take the seismic events and just fit a plane to the, to the cluster, a best fit plane to the cluster orientation and dip. I'm actually working right now on fitting fracture planes to the events based on their magnitude and based on the rock properties. So we didn't do that here, but we do need to do that for the reservoir simulation because, as I said, if you take the rock properties as measured, where all the induced seismicity is happening, there's no porosity or permeability in the basement where all of the seismicity is happening. So we have to have some way for fluids to get through that rock. And in that case, we know it's fractured. We have image logs and samples through the basement, and it's highly fractured. Thanks, Sid. What do you think could be improved in the seismic acquisition processing to improve the fault characterization? I probably shouldn't say this, but it was a very strange acquisition geometry. It was really high resolution on the receiver locations were really high resolution, but the source locations were really low resolution. I think they were like 1 to 8. So we had really low resolution from north to south, but we had high resolution from east to west. The other thing is, if your faults are all strike slip faults and they're all at or below seismic resolution, you might not be able to do it except for if you have a good sort of 3D acquisition geometry. Maybe you can run some some attribute analyses on it. We did it. It didn't work here because of the, I think because of the weird acquisition geometry. How accurate are the actual locations of the microsize? I know we're working closely with NORSAR on this, and they're coming up with some error. I think they're estimating anywhere between 10 to 50 meters. Could anisotropy in the overlying formations make it appear higher or lower? Does the microseismicity in the cluster restricted to a certain time period, or they continue to occur as long as injection occurs? They are restricted to a certain time period. We think like the pressure, there's sort of a pressure front migrating through, and then when the pressure gets to a certain sort of threshold near a fault that's oriented likely to slip, then it goes. So they're not restricted to a time period. They may be restricted to a pressure threshold. I have it, Mark. Okay, so heterogeneity seems to play a big role in the location of the microseismic events. What will be the recommendation to define this more accurately moving forward? I think that the way that we did it in the end, after we saw what was going on, I think that it's good to having a good seismic. You can do that, and also putting that. We did have those the mudstone baffles were in all of our models, and the faults after we got the better resolution seismic. All those things actually, those are the heterogeneities that influence the reservoir behavior, and our reservoir simulation engineers that we're working with at Schlumberger are getting a pretty good match for most of the monitoring data, except in the basement. And so they're waiting for me to get the fracture stuff together so that we can do that without them just turning up the permeability. So I think that basically an approach like we did would be my recommendation. Good seismic imaging, high resolution if you can't see the faults. If you can do seismic attributes, that would be good too. And make sure that you include all of those heterogeneities in your, from your well logs and your core in the model, which I think is probably what everybody does. And do the seismicity and do seismicity monitoring. So could anisotropy in the overlying formations make it appear higher or lower than they are now? They could. I don't know if it's a big higher, you know, if the error is bigger vertically than it is horizontally, though.
Well, Sherilyn, thank you. This was an excellent discussion, and I thought I'd ask if you had any closing thoughts. I
think that we learned a lot. Because I like working with the induced seismicity, we learned a lot about the reservoir from that, and that a CO2 sequestration is a technology that really needs to be developed. And I'm really happy to see that people are starting to get a lot more interest in it. You should see, as I mentioned earlier, the AAPG meeting is happening right now, and there are several sessions on CCUS.
Sure. This concludes our webinar. I'd like again to thank Peter Smealy and the entire team at ARMA for supporting our underground storage and utilization technical community here. And Sherilyn's talk will be posted on YouTube. And I thank all the participants for being here and for your active discussion.
Thank you. Bye.